All right, so what is the force of attraction between a helium electron and its nucleus if the electron is, and this is about how far it is away, right? Okay, so the nucleus of, here's the nucleus, right? The nucleus of the helium atom is going to be, what is going to be? Oh my gosh, I've got a red pen. Can I do it? It's going to be 2 protons and 2 neutrons, right? That's what they look like too. The neutrons have little ends printed on them. They don't know exactly how that happened, but it, there it is. All right, and then here's our little electron. Now the charge on the electron is going to be negative 1.602 times 10 to the minus 19th coulombs. I know that because it's an electron. It's negatively charged, right? And it's the elementary charge, right? This has 2 protons, so its charge is going to be, so this, let's say this is Q2, right? Q1 is equal to 2 electron charges, but positive because they're protons, right? So it's going to be 2 times 1.602 times 10 to the minus 19th coulombs. And it's going to be positive that, right? So now we can use our little formula, right? F is equal to K Q1 Q2 for R squared. I think the blue pen is definitely better. All right, so now we've got 8.99 times 10 to the 9th, sorry, Newton meters squared, coulombs to the minus 2, right? And then the first charge is, what is that? 3.204, is that right? I hate to mess it up, right? Yeah, we got it. Times 10 to the minus 19th coulombs, right? So positive 3.204 times 10 to the minus 19th coulombs. And then the other charge is negative 1.602 times 10 to the minus 19th. Those are coulombs, right? And then our distance is 1.7 times 10 to the minus 10th meters. And you got to square that. Don't forget to square that. Notice that the units all work out, right? Meters squared, coulombs squared, right? We end up with newtons. So this ends up being, let's see, 8.99 E9 times 3.204 E minus 19 times 1.602 E minus 19 divided by 1.7 E minus 10. Don't forget to square it. Don't forget to square the R. All right. And I'm getting that the force is very small. It's 1.5966 times 10 to the minus 8th newtons. Now, you might say, gee, that's a very tiny force, but for an electron, it's tremendous. And this was one of the great mysteries, right? Because they kind of knew the size of the nucleus and all this stuff, right? So one of the early mysteries was the acceleration of, by the way, the example's over. Okay, one of the great mysteries here is that, the acceleration, F equals ma, right? So A is going to be F over m, right? The mass of an electron is tiny. So it's 1.5966 minus 8th newtons, right? But the mass of an electron is like 9.11 times 10 to the minus 31st, right? Kilograms. So if you divide this by 9.11 times 10 to the minus 31st, you end up with a number that's like, roughly 2 times 10 to the 22nd meters per second squared, which A is a tremendous acceleration. B, as far as we know, whenever you accelerate a charge, it radiates energy. So how could a stable atom radiate energy? Anyway, I have digressed. Hopefully you didn't listen all the way to the end of this. All right.